Section 5.3, Centripetal Force. So first, let's remember Newton's second law, what we saw in the last chapter, chapter 4. It says if there's a net external force acting on an object of mass m, the acceleration that results is directly proportional to the net force and has a magnitude that's inversely proportional to the mass. The direction of this acceleration is the same direction as that of the net force. This is shown mathematically with acceleration being directly proportional to net force. They are both on top there, and inversely proportional to the mass because mass is in the denominator there. It's also often written Newton's second law as just the net force is equal to the mass times the acceleration, our F equals ma equation. Okay, so with this in mind, we can now think about how that connects to our uniform circular motion. So in uniform circular motion, there must be a net force because we have this centripetal acceleration that's always present. If we have a centripetal acceleration by F equals ma, we have to have a net force as well. This centripetal force is just the name given to the net force that's required to keep an object moving on a circular path. So the centripetal force is not actually a new force. It's not a specific force. It's a general category of individual forces that could be creating the centripetal acceleration. The direction of the centripetal force is always going to point toward the center of the circle in the same direction as the centripetal acceleration, so it will continually change directions as the object moves. And so we call this net force the centripetal force. It's equal to mass times centripetal acceleration, or equal to mv squared over r. So the main thing to note here is if we're traveling in a circle, we have to have this centripetal acceleration. And Newton's second law says that the net force then is equal to the mass times this v squared divided by r. All right. So now that we have some groundwork for centripetal force, I want you to think for a moment, what are the sources of centripetal force in your everyday life? And to think about this, consider any time something is traveling in a circle. Because if something is traveling in a circle, there must be some net inward force that we would call the centripetal force. So you can go ahead and pause and see what you can come up with as to sources of centripetal force. All right, well, let's look at some of the ones that I came up with, and I'm curious to hear if you have some others too. So one could be the tension in a cord, right? If you're twirling a rock on a string, right? As it's swinging around, these are my headphones, they don't swing nearly as well. But as that's swinging around, the cord itself has tension that keeps the rock with you, right? If you lose the tension in the cord, then the rock would just fly off. It's not going to do much. There also could be normal forces, like a carnival ride. Here's an epic example, right, where you go in and you just are standing against this platform backrest, and as it starts to spin, you get pressed into the outside. Well, you feel like you're being pressed in the outside. It turns out, actually, that force is pushing you in to keep you traveling in a circle, so you don't fly off at an angle. Other examples, static friction. This describes why your car is able to turn. The tires on the pavement exert static friction on a turn. We'll look at an example of this in just a moment. And then even the force of gravity. If you start thinking about planetary orbits or like a satellite orbiting the Earth, that's also going to be circular motion. And so gravity can be a source of this centripetal force. So this highlights once again that the centripetal force isn't a specific force, it's a broad overarching category that different individual forces can fulfill the role of this net force that is a centripetal force. Now I want to take a closer look at this static frictional force that allows you to turn your car. So if you have an unbanked curve, just a flat road that has a turn in it, the static frictional force provides the centripetal force. So what does that mean? Well, it means that if you can imagine, for instance, if the road was icy, there wouldn't be any friction there. And then you could turn your wheels and your car would not turn, right? It would just keep traveling in a straight line, which can be very scary. So we're very glad to have static friction here that allows your tires to grip the pavement and not slide across them so that you can then turn the car. So let's take a look at an example of this. So example 7, safe driving. At what maximum speed can a car safely negotiate a horizontal unbanked turn of radius 51 meters in dry weather, coefficient of static friction 0.95, and in icy weather coefficient of static friction 0.1? All right, so this is a longer example, so I'm going to try writing more on my whiteboard for this. All right, and our first step, as usual, is we want to draw a picture. So we have a car on a turn. So I'm going to draw the circular path, and I'll draw my car in here too. Cool, so there's my car. It's going along, right, with some velocity. And oh, I could also label my radius. That's the radius of the circle. So this is looking pretty good. Let's go on to write what we know and see how things go from there. So what pieces of information do they give? And then that way I'll be able to stop sharing this to make the video bigger. So unbanked turn with that radius 51 meters. And then we also get some coefficients of static friction, right? So dry weather, we have the coefficient of static friction is 0.95. And then wet or icy, even better than wet, or worse, depending on your perspective, coefficient of static friction mu sub s is equal to 0.10. All right. Note that the coefficients do not have units. That's a unitless thing, it's just a ratio. Finally, we'll fill in what we want, and then we'll start thinking about tools. So it says the maximum speed. So that tells us that we want to solve for a v. All right. And I'll add a note that this is the maximum speed, as fast as we possibly could be going. Okay, so let's stop the share. There we go. So now it's a little bit bigger for you to be able to see what we have written down so far. Now we want to think about what tools we might have here. So as I'm thinking this through, first off, I notice I'm traveling in a circle. So if I'm traveling in a circle, I automatically should start thinking about my centripetal acceleration. So A sub c is equal to v squared all over r. What other tools might be useful here? Well, we noticed that they gave us coefficients of static friction. So that suggests to me that we might care about our static friction force, right? So the force of static friction is going to be less than or equal to the maximum value, Fs max, right? And we know that we can calculate Fs max with the coefficient of static friction times the normal force, right? Where that is the normal force. Now for this one, notice we want to find the maximum speed. If we're finding the maximum speed, that means we are pushing the limit where if our car started to go any faster, the force of static friction would not be able to hold it in place, right? We wouldn't make the turn. We'd start to peel out. And so because of that, because we're finding the maximum speed, that also tells us that it's going to be the largest possible value of the force of static friction. So that's a really nice little detail there. All right, this is a pretty good start on the tools. One other one that I'd mention, since we're starting to talk about forces as well as centripetal acceleration, which we can then think about our centripetal force, I want to write down Newton's second law because it all comes back to it, that the net force has to be equal to the mass times the acceleration. And I'm just writing the general form, but it's something that appears so regularly that it's worth noting. You could also, if you prefer, write it as the centripetal force is equal to the mass times the acceleration, centripetal. All right, so this is looking pretty good, right? We have something with forces, with the force of static friction. We have our centripetal acceleration, which does involve a speed, which is what we're trying to solve for. So I think we can get this. But if we want to use anything involving forces, we want to make sure that we identify all the forces and draw a free body diagram properly. So I'm going to think about the forces acting on my car. And to do that, I'm going to look at a side view, or maybe rear view, looking from behind, say. All right, so filling in my car there, I'll get a different color for my forces. Green seems good. So we want to know the forces that are acting on this car. Well, one of them is going to be the weight of the car itself. It's pulling it down, which we know weight is equal to mg. That'd be another thing we could fill in on our note. And notice we don't know the mass in this situation, but we'll try to keep going and see how it goes. What other forces do we have? Well, because the car is on the ground, we have the normal force that's pointing perpendicular to the ground, so pointing up. Great. And then finally, we have to have a force that keeps our car moving inward, this net centripetal force. So what force is pulling inward to create this centripetal acceleration? Well, the force that's pulling inward is actually going to be that between the tires and the ground. That is our static frictional force. So now that we've identified those three forces, we can make a free body diagram. And we're going to make the car into a single point and then transcribe these three forces over here. Normal force, the weight, and the force of static friction, which we also said incidentally is the maximum. So we can make this Fs max because we already talked about that. Right. The other thing I like to add here is the acceleration. To note that there is an inward acceleration in the same direction. And that's going to be our centripetal acceleration. So I'm going to put that on the side. It is not one of our forces. And finally, the only other thing we might want to include is the x and y axes to label this a little more clearly. So plus x to the right, plus y going up. It's a little bit small, but all right. So now we can use Newton's second law in both the y and the x direction. So if we start with the y direction, because why not? Then we can have the sum of the forces in the y direction is equal to the mass times whatever acceleration we have in the y direction. So our two forces in the y direction are the normal force and the weight. So normal force, weight. The normal force is in the positive direction, the weight is down, so it's not a problem. Then we have mass times the acceleration in the y direction, which the car is staying on the road. It is not falling down or launching upward. So the acceleration in the y direction is 0, and we get that the normal force is equal to the weight. Or in other words, that the normal force is equal to mg, whichever one you prefer there. Okay, So this is a good start. Now we can look at the X direction and see how that one goes. Angle this down a little, some bit more room. So if we sum up the forces in the X direction, mass times acceleration in the X direction, we would have that we just have the force of static friction, max. And we don't have any other forces to balance it out, but that's okay because we do have a net force, and that's why we have an acceleration. So we have the mass, the car, times the centripetal acceleration. All right, so this is looking good here. So Fs max, we can plug in. It's going to be the coefficient of static friction times the normal force, which is equal to the mass times the centripetal acceleration. And note, we know the normal force because we already solved in the y direction. So we can plug in mg for the normal force because we already did that work. So we get mu s times mg, and I'm also going to plug in my v squared over r for the AC. So m v squared over r. All right. Now we actually are very comforted in the work that we've done, because even though we don't know what the mass is, notice we have a mass on the left and a mass on the right. That means we can divide by mass and the masses will cancel. Right, and so if you allow me to move over here, we'd have mu s times g is equal to v squared over r. I'm going to multiply the r across and flip the order. So I have v squared is equal to mu s rg. And so if I want to find the speed, I can just take the square root of that, both sides. All right, and now we are home free that we can plug in. V is equal to the square root of, we could start with the dry conditions, 0.95 times my radius of 51 meters times g, 9.8 meters per second squared. Right. And so if we calculate that, you should find with the dry condition, it comes out to 22 meters per second. Which it turns out, that's about 50 miles per hour. So that's a pretty good clip. What about in the icy conditions when we have a much lower coefficient of friction? Well, in the icy conditions, it drops down to 7.1. Which is a mere 16 miles per hour. So that's why you see those warnings when you're driving, like in wet conditions, recommended speed much lower, and you should actually follow them if it's wet or icy out there so that you can stay safe. That is a 7.1. Sorry, that's a little hard to see. Right, so hopefully this has helped your driving get a little bit safer, but also hopefully it's helped your understanding of how centripetal force ties in with our centripetal acceleration, and that net force can then create this circular motion that keeps your car on the road when you're going around a turn.